Okay, welcome back. So these are our kinematic equations. This is what we just derived. These are all five of our kinematic equations that we're going to need. This slide's really important. I'm sure Dr. Rowley in lecture will also give you a copy of these. These are on my own equation sheet that I use in my high school class as well. These are very, very, very useful. These are the five equations that we just derived in our last section that show us how we can measure a variable given some others, assuming constant acceleration. So we will use this first equation if we're not given distance. This first equation if we're not given acceleration. This fourth equation if we're not given final velocity. And this last equation if we're not given time. So let's go ahead and do an example, a couple of examples of problems that we might see using this method. Okay, so if you guys could all please read this problem and then try to solve it. So let's say we got a turtle in a rocket sled engaging his thrusters. Before activating them, his velocity was 2 meters per second. And after 20 seconds, he's traveled 450 meters. What was his acceleration? Okay, so take a look at your kinematic equations list and see if you can figure this one out. Pause the video, try it, and then come back here to see the solution. Okay, welcome back. Let's go ahead and try this out. So first things first, a good thing to do when solving a physics problem is to figure out what important pieces of information you have. A good place to start is looking for numbers. So 2 meters per second, 20 seconds, and 450 meters. We're looking for acceleration. Okay. Another good thing to do is to draw a picture with a number line. This might feel a little bit tedious, but trust me, as soon as we get to more complicated questions, you're going to wish you'd done this. So we have a turtle on a rocket sled. I should make him green. He's a turtle after all. Here's my turtle. And by the way, if you don't like drawing pictures, that's fine. This is not an art class. I like to make mine a little bit fun. That's bad for my shell. Like a situation going on here. Oh, this is not good. This is wrong. Poor guy. Oh no, this is fine actually. He's all right. I gave him a bit of a messed up shell at first. That's okay. There we go. So here's my turtle. I give him 3 eyes. There we go. By the way, sorry, like I was going to say, if you're not good at art, totally fine. You can make this turtle a box. Just call any object that you're looking at a square or a circle or a triangle or something. Make any person a stick person. No, your drawings don't have to be good. You just have to know what's going on. So I have a turtle. He's got rocket thrusters on the back of his sled. There's fire coming out of the back. So before he activates them, his velocity was 2 meters per second, meaning back here, his initial velocity was 2 meters per second. And after 20 seconds, he's traveled 450 meters. We want to know the acceleration. So he's gone in this direction. This velocity, by the way, was at time t equals 0. We're going to set the clock the moment that his that he activates the rocket thrusters, and we're going to stop the clock at t equals 20 seconds. So my ti is 0, my tf is 20. Basically, he was moving 2 meters per second when he turned the rocket sled on. We're going to call that time equals 0. 20 seconds later, he's moved 450 meters away. That's our final position. Okay, so let's go ahead and figure out what all of our variables are. A good place to start is just make a list of our variables. We have delta x, vi, vf, a, and t. Okay, so delta x is how far we've moved. Call our starting point 0. We're allowed to do that. We might as well. In fact, it's usually a good idea to always just call your starting point 0 because that way your xi equals 0 always. And you don't have to worry about i's and f's for x. Just call it delta x because it'll be your final minus 0 every time. So I'm going to call that delta x. I'm going to call our initial point y. You can't, or our initial point 0. You can't stop me. Delta x is going to be 450 meters. Vi, our initial velocity, is going to be 2 meters per second. Final velocity, the question does not tell us anything about what our velocity over here is. Acceleration is what we were tasked with finding. Time is 20 seconds. Okay, so let's take a look at this. We have delta x, we have vi. We're missing a vf. We're looking for a, and we're trying to find and we have time. What we want is an equation has an a in it, but no vf. So let's look back at our equations list. No vf, that's the fourth one. So we could set the fourth one up here. That's delta x equals vi t, or v naught t, plus 1/2 at squared. Okay, now all we have to do is plug and chug. Now it's easy. Delta x is 450, v naught is 2, t is 20. solving for A. Okay. So 450 equals 2 times 20 is 40. I'm going to move my math up here because I'm running out of room. That's 450 equals 40 plus 1/2 of A times 20 squared. 20 squared is 400. That's 200A. So solving this for A, that's minus 40 minus 40. By the way, the T in this, only the T gets squared, the A does not, just so that you know. So we get 410 equals 200A. A equals, sorry, divide both sides of this by 200 to get A by itself. We end up getting A equals a little over 2 meters per second squared. 410 divided by 200 is going to be 2.05. So that's how we solve a problem like that. Okay, let's try another one. A car runs a red light with a speed of 30 meters per second. The driver then gets scared and accelerates 7 meters per second squared for 10 seconds. What is their velocity after they finish accelerating? Okay, let's try to solve this. So, if a car running a red light with a speed of 30, here's my car. Whatever. It's a car. Shut off. Don't worry about it. It's a car. So this car's got a velocity of 30 meters per second. And it runs a red light, and then the driver panics and accelerates. So the driver's slamming on the gas. The acceleration's pointing in this direction too. So acceleration is 7 meters per second square. They accelerate for 10 seconds. What is their velocity after they finish accelerating? Okay, so this over here is my initial point. When the red light happens and I slam on the gas, that is my t equals 0. So this is a v naught. Then I'm going to accelerate until over here, 10 seconds later. I don't know my vf. And I'm no longer accelerating after that time. Okay, so this is my final point. So there's my situation. I'm going to call this direction positive, by the way, it's just so that we don't deal with negative numbers. That means that this direction is negative. So anything that would be pointing in this direction would be a negative sign. We don't have any, though. All right, so let's go ahead and gather our variables here. We have delta x, we have vi, we have vf, we have a, we have t. Okay, so do I know my delta x? Was I given a distance for this question? Let's read the question again. 37, 10, we're on the final velocity. No, we are not. So we are not given a delta x. We are looking for a final velocity. Okay. Our initial velocity, or our v naught, is 30 meters per second. Our acceleration is 7 meters per second squared, and our time is 10 seconds. So we have everything except for a final velocity, which we're trying to find. And we are missing a delta x. So let's go back to our equations definition. Which of these is missing a delta x? It's the first one. Okay? So we could say that Vf equals V naught plus A times T, and then we just have to plug our stuff in here, and then we could solve it for Vf. So that's Vf equals 30 plus A is 7, T is 10. Vf is 30 plus 7 times 10 is 70. Vf is 100 meters per second. And notice if you put your units in this problem, like you put that in meters per second, and this in meters per second squared, and that in seconds. Notice seconds times second squared in the bottom is going to get rid of it. Meters per second. Our answer will be in meters per second. But remember, I told you in the beginning of chapter 1, if you keep all your units in standard format, they will come out in standard format. So notice, because we put everything in meters per second, and seconds, what we got out was in meters per second. So you actually don't have to worry about units as long as you keep everything in standard format the whole time. Cool? Cool. Okay, so let's look at our final question. This one is pretty hard, actually. So please take a look at this question, try to solve it, and then when we're done looking at the question, we'll pause the video, come back later and see if we can figure it out. So let's say we have two F-Zero spaceship cars having a grand race. The blue car takes a false start and moves at a roughly constant speed, 439 meters per second for the entire duration of the race. The red car starts at rest and accelerates at a constant rate of 76 meters per second squared for the entire duration of the race. At what time from the starting gunshot will the red car catch up to the blue car? Okay, like I said, this one is a little bit tricky. Go and try this one on your own, see if you can solve it. Pause the video, come back in a minute. Okay, welcome back to our last question. Let's try to solve this one. So we have two cars, a red car and a blue car. Here's my blue car. Here's my red car. Okay, so the blue car takes a false start and moves at a roughly constant speed of 439 meters per second for the entire duration of the race. So I can say that my blue car moving at a constant speed, what does that mean? That means it is not accelerating. If it's got a constant speed, that tells us that our acceleration is zero. This thing is not speeding up. It's moving at the same speed the whole time. And we can also say then that our V naught and our VS are also equal, and they're also both equal to its speed the whole time, which is 439 meters per second and 439 meters per second. Okay, so here's our starting line. You know, they got a checkered line here or whatever. Okay, so the red car is going to start at rest and accelerate at a constant rate of 76 meters per second squared for the whole duration of the race. Okay, so we know that our initial velocity, if we're starting at rest, if it's not moving originally, V naught is going to be zero. Okay, and we have an acceleration of positive 76 meters per second squared in this direction. Okay, we want to know at what time the red car will catch up to the blue car. So we're looking for a t in this question. All right, so let's try to think about this. These two cars start from the same spot. The blue car gets a false start, so it starts with a velocity. The red car is going to be able to accelerate up to the blue car. Now, here's the thing. The blue car is never speeding up. It's moving at this constant velocity the whole time. So because the red car is accelerating, it is eventually going to pass by the blue car. So at some point here in the future, one could even say at our final position, here's our initial position, at x equals some number, at our final position, we're going to have our blue car and our red car neck and neck with each other again. So the blue car takes off immediately, getting a head start. The red car starts slower but catches up eventually. At some time later that we are trying to find in this problem, the two of them are neck and neck again. Okay, so I've got a V naught. I don't have a VF over here for this car. I don't know what his final velocity is going to be. And I can't easily find it immediately either because I don't have time. But I know what he's accelerating at. And I know what the blue car's acceleration, initial, and final velocity are too. Okay, so how do we solve this question? We have to make an assumption. And that is, at the moment that these two cars are caught up again, delta x for the red equals delta x for the blue. Right? They're both the same distance away from the starting point if they're caught up to each other. This delta x for the red and the blue is the same. So what that means is I can set an expression for delta x from the red car equal to delta x for the blue car and solve it for t. Because remember, this is happening at the same period of time. That t is the same t. T red and t blue is both amount of time since the starting gunshot. So here's what we're going to do. We're going to use the fourth kinematic equation because I'm missing a VF for red. So we could say delta x equals V naught t plus 1/2 a t squared. So for the red car, we could say V naught t plus 1/2 a t squared for the red car equals V naught t plus 1/2 a t squared for the blue car. All right, let's plug our variables from the question in now. V naught for the red car is 0 times t plus 1/2. Its acceleration is 76 times t squared. The blue car, its V naught is not 0. Its V naught is 400. What was it? 439? Yeah. 39 t plus 1/2. Its acceleration is 0 times t squared. Okay, so this is now an expression. I'm going to do the rest in black. This is now an expression that we can solve for t. Check this out. 0 times t is 0. 0 times t squared times 1/2 is 0. 0 times anything is 0. So that goes away and that goes away, giving me 1/2 76, which is 38. Yeah, 38. T squared equals 439 t plus 0 plus 0. Those zeros go away. Cool. All right, so now all we have to do is solve this for t. Here's the thing. Notice I now have an expression where every one of my variables that's not 0 has a t in it. So I can divide this by t, I can divide this by t, kill this t over here, and remove one of those squareds. So I can now say 38t equals 439. Divide both sides by 38, and we get t equals about 11 seconds. 11.55 seconds. Okay, so after 11.55 seconds of these two cars running this race, the red car will catch up to the blue car, and then afterwards, because it's still accelerating, it'll take over and win. Unless, of course, they pass the finish line before 11.55 seconds is over. In that case, the blue car will win. All right, thank you guys so